Okay. Hello, everyone. Thanks for coming to our Q-Farm seminar today. So today we have two half-an-hour talks from two Stanford grad students. The first talk is going to be by Timothy McKenna. Tim is a senior grad student in a group of Amir Safavi 90. At Stanford, he holds a bachelor from University of Pennsylvania and a master's from Stanford. He also has work experience at Johns Hopkins Applied Physics Laboratory, where he worked on hybrid systems of photonics and millimeter wave technologies. He enjoys waves and particles of all kinds, but his current projects focus on light and microwaves. He's currently working on integrated nonlinear optical devices on chip scale, cryogenic transducers, and also nonlinear optics. He's going to tell us today about his recent project on ultra low power second order nonlinear optics on a chip. And before I hand it to Tim, just a reminder to everyone that if you have questions, you can type it in the chat box, or also feel free to unmute yourself and ask your questions. Okay, Tim, the stage is yours.
Okay, great. Thank you for the introduction. So today I'm going to share some work that we've been pursuing recently in the Safavi Naini group involving second order nonlinear optics that we've integrated on a lithium niobate chip. First, I like to start with all of the people that helped with this work. We have a lot of people. I try to include most people in our group that do lithium niobate photonics in the Safavi 90 group. Hubert especially was a massive help for this project, but there's contributions all around, directly and indirectly for this work. We've also been working very closely with the Fair group, so their support has been really important for this project as well. So first, I'll talk a little bit about lithium niobate nanophotonics, just to set the stage for what we're actually doing and how we're doing it. And then I'll talk most of the presentation will really be our most recent demonstration that we finished up earlier this year. So it's really recent stuff, and I'm really excited to share it with everybody. So just an overview of lithium niobate. This is a workhorse material that we use in our group. It's a man-made dielectric, and what's unique about it, has a non-center symmetric crystal structure, which gives it many useful properties, such as an electro-optic effect, which is used for many like modulators that are used for telecommunications applications. But it's also a birefringent material. It's piezoelectric, good photoelastic effect, large nonlinear coefficients. So it really does a lot of things well. It's also a really transparent material, which is important for photonics. So not so useful properties is it's also pyroelectric and photorefractive. These things are, have been somewhat of a struggle, especially with some of the lower temperature cryogenic experiments that we've performed over the past couple of years. But for now, we're actually going to be focusing on the fact that it's a second order nonlinear material. So that's going to be most important for this talk. So this large second order nonlinear coefficient, it's about 30 picometers per volt. This lets you perform all of the three-letter acronyms you ever imagined. So if you have a three-letter acronym you wanted to do, you can do it with this material. We're going to be focusing on OPO and second harmonic generation. So for this talk and this device that I'm going to share, we operated it as an optical parametric oscillator and also performed second harmonic generation. And what's really important about lithium niobate is you can also periodically pull the crystal, which means you can basically invert the crystal domains in a periodic fashion. And this lets you achieve phase matching. And I'll share with you the technique we use to actually do this inversion, but you basically apply large electrical pulses to the crystal, and you can permanently invert these crystal domains. So this is a really important part of this project. Not going to focus on this, but in other projects that we participate in, this large linear electro-optic effect is really important, but this is not really the focus of this talk. So let's talk just briefly about thin film LN devices versus conventional LN devices. So basically, we're able to, with breakthroughs in nanofabrication, we're able to shrink traditional lithium niobate waveguides down into a much smaller mode volume, and this enhances the nonlinear interactions. The other thing that's really nice is now that we have really good pattern fidelity, geometric dispersion is also possible, so that also opens up new ideas for designs. But I think the thing I'm most excited about is this thin film LN platform. It can now be a scalable, integrated circuit platform where you can incorporate electro-optics, nonlinear optics, and linear devices all in a single circuit, all on the surface of a chip. So that's probably what I'm most excited. I mean, obviously, it's really good to be, 2 to 3 or many orders of magnitude greater than traditional technologies, but it's even more than that. It's the level of integration that's possible. And these might be slightly outdated, but there's been a lot of good recent examples from various groups around the country showing really nice lithium niobate examples. And we kind of build upon this progress for the current demonstration that I'll talk about today. Now I'll focus on some things we've done in the Safavi Naini group. So these are the popular lithium niobate platforms that we have used most. So I'll start with first, there's this, we call it LNOS. So it's lithium niobate on a silicon handle. And this platform has great mode confinement, really good microwave properties, especially at cryogenic temperatures, because you can actually just put your superconducting circuits directly on the silicon. And mechanics are supported with a release. So we have a couple of demonstrations here with lithium niobate piezo optomechanical crystals. That was some work that Wentao and many others worked on. And also we have this work by Pato and Alex Wallach, where they coupled a nanomechanical resonator to a qubit. So that was really nice work. And this was all done in this platform. Next, I'll move to LNOI. So this has a top thin film of lithium niobate on top of silicon dioxide. And you can make really nice waveguides, really good mode confinement, not great microwave properties, especially if you're trying to make superconducting circuits, because one, you have some amorphous material here, and then it's not great to have a piezoelectric handle when you're making microwave circuits. So, but this is the platform that this work used. Finally, we have this platform that's lithium niobate on Sapphire, and this is a fan favorite. So here, the optical waveguides don't need release because Sapphire has a lower index than lithium niobate, has good mode confinement, really good microwave properties, and we've used this for low temperature electro-optic microwave experiments. It's also really nice because unreleased mechanics are supported. That's this work here by Felix and Wentao, where they demonstrated photonic integrated circuits on LISA, we call it LISA. Also, Chris Sarabalis has made some really impressive unreleased mechanical devices on LISA as well. Finally, there's a large transparency window when you have lithium niobate and sapphire. These are really transparent materials that also open ourselves up to the possibility of mid-infrared devices. And I think this morning or yesterday, we posted an article to arXiv discussing some of the possibilities of using that platform for mid-IR signals. Okay, that's just kind of an overview, kind of where we stand and where this work sits within the group and in the community at large. But basically, I'm going to talk about a device that is a fully resonant device made on the surface of an LNOI chip. And here we can couple both the fundamental and second harmonic into the resonator. And it's a fully resonant system where both the fundamental and second harmonic are resonant. And that greatly enhances the Chi2 nonlinear interaction rate, which lets us demonstrate really efficient optical parametric oscillation and also some really interesting things with second harmonic generation. An overview, so we're working in the bands of 1550 and 775. For shorthand, I might call that band 780, but I'm really just talking about the second harmonic when I say 780. And this was a racetrack resonator device that we built on X-cut lithium niobate. So this lets us, basically the X-cut lithium niobate lets us have the extraordinary axis of the lithium niobate crystal transverse to the waveguide, which lets us basically have an interaction between the fundamental TE modes, the transverse modes of the waveguide. We were able to achieve intrinsic quality factors over 1 million, even with all of the processing. So this was a real, I mean, this high of quality was basically really enabled the experiments. And we optimized the waveguide geometry for a few things, but the biggest thing was the nonlinear coupling rate, which goes like 1 over the square root of mode volume. So basically by having these highly confined modes, we can have a larger nonlinear coupling rate. And when you combine that with high intrinsic quality factors, we were able to do some interesting things. So the device looks like this, where, so here's the large racetrack resonator. You can see my mouse, I hope you can. But you basically have light coming into the feed waveguide, and then we have a coupler region, which actually operates both at the second harmonic and the fundamental. So we're roughly critically coupled, not quite, but roughly critically coupled. And then the generated light and your original light will just come out the feed waveguide. So what happens is the light gets injected into this ring, it then circulates, and then say, for example, you inject fundamental light. That light will be circulating in the racetrack resonator. And then on this area, this is where we have periodic polling. So on this area, this part of the racetrack is periodically polled. So we have phase matched second harmonic generation. So this is where we have phase matched nonlinear interactions. So the second harmonic will be generated, and then it would outcouple via this coupler, and you could measure both the original light and your generated second harmonic light. So this is the device. And we made a chip, and we have probably 50 of these on the chip, but this is just one of the devices that we used in the experiment. Okay, so I mentioned that we have a periodically polled section. This is actually really important to this whole thing working. Basically, the polling lets us use fundamental TE modes, which have the largest confinement in the lithium niobate, and this lets us have the largest field overlap, which increases the interaction rate. So if you look at the effective index versus wavelength, you'll see that the black curve is for the transverse, the TE mode. And you'll see here that there's some difference in the effective indices at 1550 and at 780. And this difference needs to be compensated with periodic polling to achieve phase matched interactions. So the polling period ends up being about 3.7 microns. And this is actually a second harmonic microscope image of the thin film lithium niobate. So this shows basically what we did, where we applied a large voltage pulse to these electrodes. And if you do it properly, you can invert the crystal domain. And this is what we're seeing is, it's kind of a hard image to interpret, but this bright region, because it's kind of like an interferometric type effect, but this bright region is where the thin film lithium niobate has been pulled all the way through. So we basically pattern our waveguide in this region, and that's how we get basically high quality polling. Okay, so let's talk a little bit about the experiment. So this is our experimental setup. So we have 2 lasers because we're going to be doing experiments both by injecting second harmonic light and fundamental light. And so here we have lensed fibers, and by adjusting the position of our chuck, we edge couple into the end of this chip. So basically, by adjusting the location of the chip, we can either move the chip up to be edge coupled into a 1550 laser, or move it down into a 780 laser. So depending on which one you do, on the output, we actually collect both wavelengths, and then we split them, we filter them to independently detect both wavelengths. And this lets us see things like this. So here's a very typical experiment in second harmonic generation, where we'll sweep the laser. So these are tunable lasers we normally use. We'll sweep the laser from like 1540 to 1554, and the red is the pump transmission. So this is normally what you would expect with a resonator. You'll see dips where you couple light into at the resonances of your racetrack. But what you'll also see is peaks where second harmonic generation is resonantly being enhanced. So you see peaks where the SHG takes place. Now you can also operate this in a different way, where now you pump at the second harmonic and here you'll see peaks where you form parametric oscillation. And you'll notice that, you know, not all of these peaks are here. That's because that's a thresholded process. So basically, either maybe the modes had slightly lower Q in these areas, or the modes just weren't aligned up. Like I mentioned, that these are resonant processes and they're fully resonant. So you need your pump mode and your signal mode to basically be at the right wavelengths. So looking more at the OPO, this is just an example of what we measured. So we measured a parametric, if we just look at one of those lines basically, and if we sweep the on-chip power, we can measure the generated OPO output power. And we see that basically the threshold is around 70 microwatts. And this was achieved at room temperature. So we didn't really have to temperature tune very much at all. You know, we tune a couple degrees from room temperature just to get the modes to line up, but that's really all we had to do. And I'm pretty excited about threshold numbers like this, because it means like we probably have the opportunity with a particular power budget to integrate many, many devices on a single chip. And that's where things can get really interesting. This particular data set was from a non-degenerate operation, but I'll show some degenerate operation later. And this is great. Like we were really happy to see this threshold, but there are actually some other really interesting characteristics of the OPO that I want to now explain. We kind of have to do, well, we don't really have to do math. We just have to look at some cartoons. So try to ignore all these subscripts and superscripts and all this stuff. Basically, we have a couple of mode equations where these equations really just show how the fundamental mode amplitudes couple to the second harmonic mode amplitude. So all we're really focusing on is on the fact that we have the fundamental and second harmonic coupled through this G factor. We normally use the variable G to denote the coupling rate. In our case, it's about 150 kilohertz. So this shows coupling. And then we also have drive terms. Depending on whether we're looking to do second harmonic generation or parametric oscillation, you would drive the fundamental or second harmonic. So in cartoon form, this is what we have. We have a bunch of modes at the fundamental, a bunch of modes at the second harmonic, and they're all coupled. Now, they might not all be coupled effectively, but you can see that this is what these equations represent. But let's look at specifically how you get parametric oscillation in this system. So you can basically look at the A mode amplitudes. You basically can look at the evolution of the A mode amplitudes, and we write it in like a matrix form like this. Only pay attention to the diagonal terms right now, but basically what we see is that the intercavity population at the second harmonic, that's the B modes, basically as that increases, there's these off-diagonal coupling terms increase. And as they increase, they can actually increase to a point where the eigenvalue of this matrix becomes positive, which means you have an instability, which means you have oscillation at the omega M and omega minus M modes. And this cartoon kind of shows that, where you basically have omega M and omega minus M coupled through the intercavity population of the SH pump. Now let's pay attention. Now we'll talk about the diagonal terms. So again, so when you look at the instability condition for this, which is basically the condition for oscillation of your parametric oscillator, and by the way, this is all CW, like everything in this whole presentation is CW. I think maybe the next presentation is going to involve a lot of really cool multi-mode stuff, but this is all CW, so you don't have to really worry about multi-mode things right now. But basically, here we have, the term I really want to focus on is this term. I haven't explained any of these variables, but it's really important because when you have a fully resonant system, we're basically going to see that the oscillation threshold involves a lot more things than just the pump power. So let's go through all of these variables. So it involves the laser detuning. So the laser detuning I call big delta, and this is just how far your laser is from the center of the second harmonic resonance. We then have what's called the modal detuning mu, and this is basically the difference in resonant frequencies between the fundamental and second harmonic modes. And we adjust this by fine temperature tuning. We only have to go a degree or two, but it's basically from room temperature, but it's fine temperature tuning that controls this. And then you have dispersion in your resonator, where we have this dispersion parameter, zeta, and this just describes how the free spectral range changes as a function of frequency. So that basically is all of the terms here. And then we have our M number. We just call this basically our mode number. So that's all that is. So basically, the mode that's going to have the lowest threshold, the fundamental mode with the lowest threshold will be the one that minimizes this term in the box. So let's see how that looks in another cartoon. Basically, so here we are, where we're going to see how the output OPO spectrum changes as a function of pump detuning. And I want to emphasize that that last slide I showed and everything I'm talking about is possible because we have a fully resonant system. It's possible because both the pump mode and the pump second harmonic mode and the fundamental modes are fully resonant. So here we see when delta is large, when our laser detuning is large, you need a larger M number to compensate for it, to minimize this term, because that, if you choose M to minimize this term, it's the mode number M that will oscillate first. So the dark indicates that these modes are oscillating. So if we then change our detuning to make it smaller, different modes will preferentially oscillate. And you keep going, you keep tuning your laser closer to the center of the 780 resonance, and you just basically see this shift until finally you'll get degenerate operation. And for this example, I've assumed that the modal detuning is perfect, that mu is equal to 0, but I'll show some real life examples of what happens when mu isn't perfect. Then if we keep tuning past, it's still going to be degenerate because the M equals 0 still minimizes this quantity. So this will preferentially oscillate, but the threshold is going to be higher because one, the boxed term is going to be larger, but also this B0 population, I haven't really talked about this, but this B0 squared is the number of intracavity pump photons. And as you tune your laser away from the resonance, you'll basically be injecting fewer photons into the cavity. So the threshold is just going to be higher. Okay, but let's see what it looks like in real life. So thanks for bearing with me. We did a little bit of math, but now we're back to an experiment where you can see basically exactly what I described, where in this data, where we tuned the pump over the resonance. So the blue will be the 780 resonance. In this presentation, blue is always 780 and red is always fundamental if you haven't caught on, but the red will be the OPO output power, but we also spectrally resolved this output power to show exactly what the cartoons show, which is that the modes that oscillate, the signal idler pair that oscillates is a function of laser detuning. And this lets us basically just change the laser detuning over like 500 megahertz here. And we see signal idler pairs that tune over 1 terahertz. So this is really cool because you can now tailor the emission spectrum of your OPO without large temperature tuning and without very many other considerations. We also looked at the impact of mu. So this is now a little bit different. So now instead of just sweeping the laser detuning, we're now looking at adjacent modes. And like I said, remember this mu is the modal detuning, and I mentioned that we use temperature tuning to do this. Well, there's a little bit of dispersion in the cavity. So just because, and these are pretty high Q modes. So just because, well, you might optimize the temperature for one mode, but that doesn't mean the adjacent mode is optimized basically. So the mu might be somewhat non-zero, or you might want it to be non-zero. But here you can see that clearly the fact that the range of M numbers is changing from adjacent mode to adjacent mode, that tells us the mu is changing. So we can basically predict that for this last mode on the right, the mu must be the largest because it required the largest M number, mode number to compensate for that mu. So this is really nice to validate some of the theory. We also were able to achieve degenerate OPO operation where we make mu close to 0. And here you can see at 0 detuning, we get degenerate operation basically. And we can talk about more why this isn't fully filled in. Maybe I'll show you a simulation at the end of the presentation, but basically there's disorder in the system in terms of the Qs. Okay, So that's the OPO. I hope we're all happy because we're actually going to be building on some of those concepts to show a cascaded OPO. But first, we need to talk about second harmonic generation. So basically, we're going to focus on the white region of this plot. This is showing as you sweep the input pump power, how the second harmonic power changes. So here you see if you increase the power, you get more SH power out. This is completely expected, and it's fully modeled by a two-coupled mode theory where you just have one fundamental mode and one second harmonic mode. You basically have this picture. You know, what's interesting also, that the efficiency is this green curve. And you'll see that, you know, the efficiency doesn't grow infinitely. Instead, it kind of has this saturation effect. This is actually a feature of resonant SHG systems, where as you increase the pump power, you're inducing additional two-photon loss, basically nonlinear loss. And that's a good thing. That's what you want. It's not the bad kind of loss. It's the good kind of loss. But what that does is it basically changes the coupling efficiency of your fundamental in your feed waveguide. It changes the coupling efficiency to your ring, because now you have this additional loss. So even though your ring, your bare cavity was critically coupled, once you have additional loss, you're actually effectively undercoupled. So if you want more efficiency, you would just design an overcoupled ring. That wasn't really the purpose of this work. I'm just stating this. Let's now look at this yellow region. Here we see the efficiency now really starts to go down. So this is kind of interesting, and it can be explained by a cascaded OPO process where we basically generate enough second harmonic light from pumping at the fundamental that second harmonic light then triggers additional oscillations back at the fundamental. So that accounts for, in this light yellow region, that accounts for the decrease in efficiency. You keep going to the dark orange. This is where like third order effects start taking place, which we didn't study in this particular work. So we're actually going to focus on parts of this curve up to about 1 or 2 milliwatts, where second order effects are the dominant, account for the dominant physics. So let's look at this cascaded SHG in a little bit more detail. And so to understand this, we're going to have to think back to the conversation we just had about the OPO. But basically, let's see how the line shape evolves. Let's just first qualitatively see what's going on here. So the red is our pump mode. This is at the fundamental. So you see at low powers where you're not really converting much light, you see a basic Lorentzian line shape. This is pretty normal. If you keep pumping at the fundamental harder and harder, you'll see a dip form, and this is no longer a Lorentzian line shape, but this dip is still completely explained. It's completely explained by the two-coupled mode theory. So there's been no cascading effects so far. And actually, if you kind of squint, there is a dark line on this plot, and those are the theory curves. So you can see that the theory really does match these experimental line shapes very, very well. Okay, if you keep going and venture into this dark yellow region, you'll then see that line shapes become asymmetric. Let's especially pay attention to the second harmonic line shape, which is these blue curves. So we see after a while, for negative pump detunings, so that's detunings to the left of this black line, we see that the second harmonic power starts to drop. And this drop is what we measured in our efficiency curves. In the curves from the last slide, it's this drop that accounted for some of this drop in efficiency right here. So what we're looking at is we're seeing that there's a drop in power and it's a function of laser detuning. Well, this sounds pretty good because we just looked at parametric oscillators where you pump the second harmonic, and we saw that the modes that oscillate they actually are a function of laser detuning. So, okay, let's explain this a little bit more. So this happens around a 600 microwatt threshold, this cascaded parametric oscillation. And basically the condition, the OPO threshold condition favors negative pump detunings since our dispersion parameter zeta is actually negative. So if you look at this term here, if zeta is negative, I know the variables are a little different. That's just because we're doing, we're pumping at fundamental. But if you look, if this zeta is negative, then it's for basically negative pump detunings that you minimize this quantity. And that's exactly what we see here. For negative pump detunings, we will basically be able to surpass the oscillation threshold and start to oscillate back at the fundamental. And that's what this is now experimental data showing this. So here we have the SH response, and I call these plateaus. See this plateau right here? This is the region where you're converting second harmonic back to your fundamental. And we were able to spectrally resolve this conversion process. And we saw for mode numbers 8, 9, and 10, we were able to record that emission back from the second harmonic back to the fundamental. Now, I anticipate if we did this measurement in a much broader frequency span, we would have been able to see more modes oscillate much further away from the m=0 mode. But time didn't really allow us to make such an enormous measurement. But this is really interesting, and it confirms it confirms what's happening on this plateau region. So we also did a simulation to confirm this, and we see something very, very similar. So again, the SH line shape develops this plateau, and in the region of the plateau, we can see that we're now oscillating at these fundamental mode numbers. So the simulation matched our experiment very, very well. It even gave a threshold very similar to our experiment. So here you see, as you increase the pump power, the line starts to change and you form a plateau just as we did in our experiment. And for this particular simulation, we assumed 1% disorder in the quality factors of our fundamental modes. And that's why you kind of get a little bit of sparsity in this spectrum. That's because there is going to be some difference in the line widths of all these modes. So you might not actually meet threshold for certain mode pairings. Okay, so in conclusion, we've talked about an optical parametric, a fully resonant optical parametric oscillator that we made on an LNOI chip. And we showed that because it's fully resonant, there's really interesting tuning behavior where both the modal detuning and also critically, the pump detuning really changes the output spectrum of the OPO. We then showed really efficient second harmonic generation. And because our processes were efficient enough, we could then demonstrate cascaded OPO, where a lot of the concepts from the driven OPO carried over. So we were able to understand how the detunings worked in the cascaded OPO case. So yeah, this has been a lot of fun to work on. It's been really fun to present to everybody. So I'd like to thank everybody in the audience, but also all the support we received from various funding agencies, because we can't really do it without that. So yeah, thanks everybody for your attention.
Thank you very much, Tim, for the very interesting and clear talk. We have a minute or two for some questions. Just, oh, I have something in the chat box. So Mark is asking, could you go to an overcoupled resonator at opioid degeneracy and look for squeezing?
Yeah, we definitely could. That's a really good idea. Yeah, no, definitely. So I think what's really important, like I said, we were actually focused on the emission spectrum, but the context of this question is that when you operate an OPO subthreshold, you get squeezing. And this squeezing can be very large for overcoupled resonators. So that's a great question. And I think this type of device can really open up possibilities for a lot of applications in quantum computing and other things where you can generate squeezed light on a chip. So that's a really good question.
Any other questions? Just feel free to unmute yourself if you have a question.
Yeah, I have a question. What would be the reason for the disorder in Q factors?
Oh, sure. I mean, there's a lot of things that go into this. One is there's actually a couple different types of disorder, but basically when we make these resonators on the surface of a chip, we kind of noticed that it's probably not as clean as a crystal in between two mirrors. Instead, different modes will sample some of the imperfections of the fabrication differently. That's one thing. So we kind of normally see our intrinsic Qs vary by like 1%. Another thing that can be important is the fact that these waveguides are not single moded. In fact, at the second harmonic, there are many modes. So this can cause different types of mode mixing, which can reduce the Qs. If you couple to a lossier mode, you can reduce your Q a little bit, but it can also slightly push the frequency of these modes. So that also can reduce, that also can basically change what modes oscillate, because now you have disorder a little bit in the frequency, the absolute frequency of the mode, but also in their Qs. Does that give you an idea of what these devices are like?
Yeah, thank you.
Yep.
One question, is it possible to use some of these tuning mechanisms to, say, continuously tune from degenerate to non-degenerate operation and back? I'm sort of thinking like in the context of OPO Ising machines, for example. You know, the non-degenerate operation has sort of a continuous phase freedom, whereas the degenerate one sort of has this phase locking behavior. And that could be like one idea that could be useful for changing the dynamics of these kind of network systems.
Yeah. So it's actually really easy to go between degenerate and non-degenerate, especially because what we showed, if I go back a couple slides, basically like, okay, like here, for example, I know this is a little messy. We were taking this data pretty quickly, but basically just by changing the pump wavelength by a little bit, just by tuning that a little bit, you can quickly go from degenerate to non-degenerate. So that's kind of like this picture here. You can be degenerate and non-degenerate pretty easily with just tuning the laser. You don't technically need to tune the temperature.
And so there I see that at least on the time scale of the characterization, it looks like a discrete jump. But I guess when you actually cross that threshold from degenerate to non-degenerate operation, there's presumably some smooth dynamics that's happening there. What are the prospects for being able to sort of control that transition?
That's really interesting. I'm not sure. We haven't modeled those dynamics, but that seems like it could be really useful. So yeah, maybe we should talk about that.
Yeah, thanks.
Okay, we are a bit over time, so maybe we can move on. And so if you have more questions, maybe we can email each other, or we can do it at the end of the session if you want to stick around. Okay, so thanks, Tim, again for the nice talk. Let's go to our second talk. So our second speaker is Ryotatsu Yanagimoto. He's sharing his screen. Okay, so Ryo is a PhD student in applied physics working at Haida Mabuchi's group. He got his bachelor in applied physics at University of Tokyo. He's interested in AMO physics and quantum photonics, but his current research is focused on understanding quantum dynamics of broadband optical photons in highly nonlinear systems. The stage is yours.
Yeah, thank you. Thank you for the introduction. So so the topic of today's talk that I'm going to make today is quantum dynamics of ultrafast nonlinear photonics. So it's about sort of, so Tim made a really great talk about the developments in the highly nonlinear nanophotonics. The type of work that I'm working on is really about like what happens in the domain, like limit of high nonlinearity and the weak pump, so that we get a lot of like nonlinear interactions happening among multiple frequency modes. So let me get started. So yeah, I just wanted to point out that like this work has been done under a collaboration with a lot of people, and especially I'd like to thank Edwin, who is like online now, for like a lot of like insightful comments and advice and work. But so okay, so let me just like start from a very brief overview of the intro. So optics has a lot of interesting quantities, like benefits, when we think about it as a carrier of the quantum information or the or a medium for the quantum engineering. So it has a, its wavelength is pretty short, so we can do on-chip implementation. It has a very high bandwidth, so it has a lot of information capacity. And also the large energy of the photon allows us to have a room temperature operability, and also it supports long-range communications. But when we start to sort of use it as a all optical platform for quantum engineering, we start to find a problem of low nonlinearity compared to the loss rate. So what it means is that when the ratio of the nonlinearity with respect to the loss rate is not greater than 1, then we can't really see a sort of exotic quantum states that have like a lot of utilities for quantum engineering. So the strongly interacting regime is generally referred to as a regime where the nonlinear rate is faster than the rate of the loss. Okay. So we want to get to this regime. So what are the recent developments? So it seems like, so there's been a huge rapid development in the ultra-low-loss nonlinear nanophotonic platforms. The team made a really great talk. I'm very excited about those developments, that like the nonlinear rate is going up and the linear loss rate is really going down. In addition to that, we can think of going to the shorter wavelengths operations so that the nonlinear rate is further enhanced. And also, we can think of like that the advances in the dispersion engineering allows us to operate these lights in the pulse domain, which allows us to have a higher peak intensity, then which enhances the nonlinearity. Also, we want to think about the sort of non-trivial amount of excitation in each pulse, so that large number of like photons interacting with each other enhances the nonlinearity further. So combining these sort of stars, like we have shown that it seems like just in terms of the figure of merit, these nonlinearities seems to be getting to the point where we can implement a critical gate for continuous variable quantum information in an all optical manner. So it's what I want to point out is that it seems like thanks to the rapid developments in the experiments, we seem to be getting to the point where we might be able to observe these highly nonlinear quantum effects in the real life in an all optical manner. Okay, but these sort of potential, like despite the fact that it has a huge potential, it comes with a huge modeling and theoretical challenges that we want to tackle. So let me explain that. So traditionally, the quantum optics, like the most of the quantum optics literature, rely on this single mode or like few mode picture of the quantum optics, where we have a nice-ish resonator in which we have a nonlinear medium and light is confined. So we have two modes that experience highly quantum dynamics. On the other hand, when we think about this broadband quantum optics or ultra-fast nonlinear optics, they have a very dynamical feature that sort of supports large number of frequency modes. So this is like some supercontinuum generation done by the multi-phase group and Mark. And as you can see, it spans an octave of frequency range, meaning that thousands of frequency modes are involved in this highly complicated dynamics and producing this spectral broadening. So despite the fact that these two pictures are talking about the same thing, just photons, they look very different from each other. And as we get to the point where this quantum nature of the photons kicks in to this domain, no ultra-fast nonlinear optics, we do need to think about the modeling in a very different perspective, right? So the idea here is as follows. When we think about the photonic field, we can think of it as an excitation of the bosonic field, like quantum field in the 1D domain in this continuous manner. So the Hamiltonian should really take a form of a sort of interacting bosons in the 1D space. And in order to really understand what's happening here, we need to synthesize the ingredients from the many-body physics, because the Hamiltonian takes a form that has been studied in the many-body physics. And also want to think about the CV quantum information, because they experience sort of a highly quantum dynamics. And also because they happen in this multi-mode regime where we have a lot of frequency modes involved, we need to also include the ingredients from ultra-fast nonlinear optics. So then let me just get to this overview of my talk. So first, I'm going to talk about the Broadband Pdc or parametric down conversion, or in some sense, it can be seen as a optical parametric oscillator in a doubly resonant cavity. The thing is that this study, the quantum study of Broadband Pdc, allows us to see really like it highlights the need to take into account these broadband effects. And as I'm going to show soon, this physics really shows a dynamics that is completely different from the semi-classical predictions. Okay, then we also talk about the prescription based on the MPS-based numerical frameworks, which allows us to perform full quantum simulations of these pulse nonlinear optics in the quantum domain. And then I'm going to summarize the work. Okay, so let me get started from here. So yes, Tim did a really great talk on like about this process of the parametric down conversion. So let me go kind of brief here. So the idea of the parametric down conversion is that when we have a Kaito nonlinear crystal and we send in the pump photon, it splits into two photons, signal and hydra, in a way such that they fulfill momentum conservation. Okay. Then because of this momentum conservation, we have this entanglement between signal photon and hydra photon, and they can be used for some applications, for instance, heralded single photon sources for quantum information. So most of the experiments, like current experiments, are performed in the semi-classical domain of the PDC, where we send in a lot of pump photons into the nonlinear crystal to compensate for the weak nonlinearity of the system. And as a result, we get most of the pump photons being not depleted, but we still have like one or few photons in the signal mode and the hydra mode. So in this semi-classical domain of the PDC, pump field is generally assumed to be undepleted. And also the conversion efficiency is pretty low because the pump just remains there. So the question that I'm gonna ask here is what happens in the quantum limit of this process? By quantum, I mean making the pump field weaker and weaker and make the nonlinearity larger and larger so that they balance each other. So we have in this limit, we have a strongly interacting PDC where we send in almost like a few photon level of pump field into the Kaito nonlinear crystal. And what's gonna happen? Like what happens? That's the question that I like to answer here. And as a result, I am going to show that what's coming out from here looks very different from anything that we would expect from semi-classical intuitions of parametric down conversion. Okay, so a quantum Hamiltonian that is sometimes used in the field to describe such strongly interacting Kaito nonlinear interaction is this innocent model of the single mode Kaito nonlinear resonator. So for instance, when you have a sort of single mode nonlinear resonator, you can model the system as this, where A is representing the annihilation operator of the signal photon or the fundamental photon, and B is representing the annihilation operator for the second harmonic. And as you can see from this Hamiltonian, if you send in a single photon pump into the system, then it leads to a Rabi oscillation. And depending on the detuning, you get like different amplitudes. But the feature of this oscillation being sinusoidal is pretty persistent, and it's always the case. But what I'd like to emphasize here is that when you have a resonator that is not really single mode, like unless you pay a special attention to the fabrication so that it ensures the single mode interactions, there are different frequency modes and this picture becomes kind of too naive. So what's the more sort of accurate picture of the way how photons interact in these nonlinear mediums? So let's think of a straight waveguide first, right? Like, because that's a part of the waveguide that is forming a ring resonator. And when you think about it, we have a continuum of pump field that is continuously interacting with the signal modes in this continuous time manner, right? So in some sense, it's like interacting bosons in the 1D system where they sort of interact via this Kaito nonlinear interaction. And because the system has a dispersion, we have bosons with mass right? So these signals and pump, they have different mass, and they interact in a way such that they preserve the momentum, or like pump photon splits into two signal photons. As a result, we have a Hamiltonian, which looks more like a many-body physics. So we have a signal band and the pump band where the curvature is corresponding to the mass of the particles, and they interact with each other via this nonlinear interaction. And this picture also applies to the case when we have a doubly resonant OPO where the size of the system is large enough to support, like, let's say more than 20 frequency modes. So in general, this Hamiltonian is like intractable. Dynamics under this Hamiltonian is very complicated, but we can limit our interest to the single photon pump case, where we can sort of derive this interesting analogy to get sort of to understand the essential features of the physics without sort of even going through a lot of like math. Okay, so the idea here is this. When we have a pump photon that has a momentum K3, it splits into two signal photons with momentum K1 and K2, such that they fulfill the momentum conservation. But as you can see, the K3 has only 1 degree of freedom, it's just K3, but this K1 and K2 can partition this entire K3 into like whatever combinations of K1 and K2, right? So it has another degree of freedom that is continuous in the signal mode. And because of the dispersion, they all have different energies. So as a result, we have this discrete pump mode coupled to a continuum of signal mode that is forming a quadratic form. This unique interaction structure of discrete continuum interaction has also been identified in the atomic system, where you have an excited state and it's coupled to a continuum of ionized states. And it's called all ionization, where an atom in an excited state sort of ionizes through a unitary process. And by exploiting these features, we can denote this like gap as a phase mismatch. So it's experimentally corresponding to the energy difference between this part and the bottom of the continuum. So what happens like as a result of this specific sort of like this unique form of the interaction, right? So in the domain, in the regime where this pump photon, the energy of the pump is higher than the bottom of the continuum, what happens is that we get to excite. So this is the non-degenerate OPO regime. Like we have a, this discrete state is coupled to a middle of the continuum, so that in the momentum space, we have two peaks. And in the phase, in the real space, it is corresponding to two wave packets moving away from each other. And because of this interaction, right, because this interaction is dissipative, if you look at the pump photon population, it decays exponentially. It's like we have a qubit that is coupled to the vacuum with the continuum of mode, and it's coupling it's dissipating into the vacuum. Or in the other regime where this pump state is well below the bottom of the continuum, which is corresponding to the degenerate operation among OPO, we get to see the feature that this momentum has a single peak. And because of the dispersive nature of the coupling, we get some oscillation. So the coherence lives longer than the other case, but it decays yet. And that decay is subpolynomial, which is pretty interesting. It's a characteristic feature of the non-Markovian decay dynamics, because I mean, now we are not coupling to the middle of the continuum. And there's another point where some non-trivial quantum interference leads to the 100% pump depletion within a finite amount of time. So just to sum it up, in the single mode picture, we have these nice sinusoidal oscillations. But when we start sort of thinking more carefully about the degrees of freedom that the system has, and in principle, the system can excite these degrees of freedom, we get to see the features that are qualitatively different from what we would expect from either from the single mode theory or the semi-classical predictions. Okay, so I hope like I have motivated the development of full quantum treatment of these broadband quantum systems enough, so that let me just talk about how we can do the simulation, like in the real life, like when we have a device, experimental device, and we want to understand what is the full quantum properties of these devices, what are the numerical framework that we can always go to as a generic purpose software. So first, let us consider how to model this Hamiltonian in the Chi3, let's say the Chi3 nonlinear waveguide to be concrete. Okay, so we have this Hamiltonian, but for the numerical simulations, it is nice to make it discretized, right? So we split this space into finite size bins, and basically write down each interactions as interactions between these bins. And it turns out that the surface modulation term becomes being intra-bin surface modulation. And we have these dispersions being hopping interactions between spatial bins. And although this Hamiltonian looks good, we can't really naively do the simulation of this system because we have a lot of frequency modes involved. Sorry, a lot of modes involved. And also we have a lot of photons, we could have hundreds of photons in this pulse, and they all go through non-Gaussian dynamics. So if you just naively plug in this equation into the QDIP, for instance, it just explodes very quickly. So we need to be a little bit smart. We need to be a little bit innovative about how to sort of exploit specific features, unique features of this system to facilitate numerical evaluation. Oh, and they get all entangled because they interact. Okay, so the thing is that recently, Google did that quantum supremacy experiment, but it took them a lot of time and efforts to really make it intractable for the classical computers. So in fact, it is not always the case that whatever quantum system is intractable. Actually, it's a little bit difficult to make it so. And the point is that we have we need three different ingredients and simultaneously fulfilled to have an intractable quantum dynamics. So one thing that is important is this entanglement. And we can also the number of modes and the non-Gaussianity of the quantum state. So when we only have the entanglement without having number of modes or the non-Gaussianity, let's say we have a continuous variable EPR state, or when we have a lot of modes, but not having much of the quantumness, then we have classical ultrafast optics. And when we don't have a lot of modes, then it's just a single mode simulation, like a cat state. But we can go a little bit further, right? So as long as we give up on one of the component, the simulation is still feasible. So the idea is that when we don't have much non-Gaussianity, but have a lot of entanglement and the number of modes, the state looks like a CV cluster state, for instance. Or when we don't have a lot of modes, then we can just still numerically diagonalize the Hamiltonian. And this corner is the most interesting thing in this context. When we don't have much of entanglement, but have a lot of modes and they are all non-Gaussian, it has been known that the matrix product state representation can exploit this feature to facilitate efficient quantum state representation. And also it is known that 1D many-body quantum system heuristically exhibit limited amount of entanglement. So as a result, we can claim that, okay, we have optical pulse, but if we model it as interacting bosons in the 1D system, then we can exploit this nature of the 1D quantum system of having limited amount of entanglement. And then we can express these quantum states as an MPS. So the numerical simulation techniques that can be used to simulate these features, these states. For instance, for this case, we can use the truncated Wigner simulation or semi-classical simulation allows us to capture these quantum states. Here we can just use the QTIP and can fully diagonalize the Hamiltonian. And in here, Vidal has come up with this super cool trick called time evolving block decimation, which allows us to evolve MPS in time under a certain many-body Hamiltonian. So let me just quickly talk about how the MPS is defined and how it can be evolved and what are the interesting features that we can find out of the simulations, okay? So the starting point of our MPS is this Schmidt decomposition of quantum states. So let's think of a partition of the system into subsection A and B, and we think of the Schmidt decomposition of the quantum state, okay? And as a result of that, we get these Schmidt weights, and when we apply it to mode 1 and the rest of the system, we get this decomposition. but we can basically cascade this process until we get the complete decomposition of the entire states into the products of these low rank tensors. Okay, so pictorially, it looks like this. We have the entire quantum state where all the quantum state information is encoded in this n rank n tensor. We decompose it into the forms of a product of rank 3 tensors. And this Schmidt weight, as if you remember here, this Schmidt weight is related to the amount of entanglement between mode A, section A and B. So if the entanglement between A and B is limited, then we can have a limited Schmidt rank here, which makes the representation more efficient. Okay. So here's the summary. Like we have this 1D quantum system, we encode it in the as a matrix product state, and then by looking at the Hamiltonian takes a form of surface modulation happening on each beam, and hopping interactions exist between different beams due to the dispersion. So we can encode this evolution as a quantum circuit, like of this form, just 2 gates operation, 1 gate operation, and run them in time. And Vidal has shown that using time evolving block decimation, we can do the simulation pretty efficiently. Okay, so this idea of using like MPS for bosonic simulation is not completely new. In the many-body physics, people have used it for a very long amount of time. It's been a very established technique in the field. But a problem in applying this MPS trick for what we are interested in, let's say the quantum information processing, or let's say the quantum engineering, is here, is shown here. So the in the many-body physics, they focus more on the particle picture of these particle aspects of photons. Right? What it means is that what they are interested in tends to be n-particle correlation functions of these particles. So given that you find a particle here, like what's the distribution of the other particle? Something like that. But in the quantum information, or like this quantum engineering picture, we are more interested in the oscillator aspects of the photons, which means that something like Wigner functions of a quantum nonlinear oscillator, things like that. So let's say when we have a pulse supermode, the question is, what is the quantum state that is populating a pulse that is propagating in a nonlinear waveguide? Due to the non-local nature of these states, like pulses, traditional MPS framework has a difficulty in sort of answering these questions. The traditional framework cannot answer the question of what is the Wigner function of a quantum state that is populating a certain pulse supermode. So that's the question that we addressed in this work, where by sort of constructing an MPS circuit that demultiplexes non-local supermodes into local beams, and we can take a partial trace afterwards to get the full quantum information of the state that is populating, let's say, this supermode. And you can do that for many arbitrary number of modes. So this is a numerical simulation result that is showing the way how quantum solitone, like optical solitone, propagates in a highly nonlinear Chi3 nonlinear waveguides. So this n is representing the number of photons in the solitone mode. So classically, it should stay stable. But as you can see, quantum effects kick in and the pulse form distorts as it propagates. And also, if you look at the quantum state that is populating this solitonic pulse mode, it shows these Wigner functions with a lot of negativities. So the MPS framework has allowed us to sort of capture all the non-Gaussian quantum features that are well beyond the semi-classical treatments, and has allowed us to basically like answer questions about what's the sort of concise description of the evolution of the state in these pulses. So it's like, oops, sorry. So we can in fact show that these evolutions can be well approximated as a single mode Kerr dynamics. So an optical solitone, although it's populating in this, it's living in this very high dimensional space, there's some sort of quasi single modeness of the dynamics, which allows us to see it as a sort of flying cavity, flying nonlinear cavity that is sort of pretty well closed within itself. So to summarize it, MPS framework has enabled us to perform full quantum simulations, including the non-Gaussian features of these highly quantum pulse propagations. And our algorithm has allowed us to sort of, for a given MPS, answer questions that are relevant for quantum engineering. Okay, so as a summary, as these fields of like quantum nanophotonics advances, it's getting to the point where we want to think about carefully what are the broadband non-Gaussian dynamics of these photons and how it affects the observables in the experiments, and whether we can sort of harness it for something useful. And as I've shown, semi-classical treatments that have been heavily used to model these systems are going to even sometimes fail in capturing qualitative features of the dynamics. And as a prescription, MPS-based technique could serve as a sort of general purpose numerical framework in which to unravel these broadband photon dynamics. And yeah, and I think like there are still a lot of things that we don't understand in this sort of emerging edge of this quantum optics. And yeah, proximal experimental and theoretical collaborations is going to be very vital to sort of explore the future of this field. So yeah, thanks a lot. And I'd like to thank my collaborators once again. And yes, I'm happy to take any questions.
Thank you very much, Ryo, for the very interesting presentation. Oh
yeah, one last thing I wanted to say was that sort of related to the talk of teams, our method, like this MPS method, is also compatible with the Kaito nonlinear system. It comes with a little bit of an overhead, but just wanted to point out that as long as the system is 1D, it can deal with that.
Cool. So we have time for questions. I see one question in the chat box from Sotvik. So he's saying, thank you for the talk. What is the time gate number complexity of the demultiplexing circuit?
Sorry, once again, please, for the last part of the sentence.
What is the time gate number complexity of the demultiplexing circuit you have?
Oh, okay, I see. So yes, I hope I understand the question correctly. So let me wait here. So if you look at the circuit here, in order to demultiplex one supermode, it has to apply one mode gate and n-1 two mode gates to the system. And the application of each gate has the complexity that scales cubically with respect to the dimensions of this MPS. But in principle, like these operations are the same as the ones that we already used in simulating the dynamics of the system. So it's just the same operation, but operated in a very different way. So the complexity is really like, if we want to demultiplex, let's say n supermodes, it is going to be n times large n, so that it scales linearly with respect to the size of the system and the number of supermodes that you want to demultiplex.
Thank you. Any other questions? You can also unmute yourself and ask questions. I have one quick question about your, well, I asked you this before probably, but about the broadband PDC
Sure.
part that the input, the pump of the system, you consider single photon. I guess I was wondering if you can see a similar signature using weak coherent state as a pump.
Weak coherent state as a pump, yes. So although we see this dynamics, like this theory is based on the single photon pump case, the dynamics of the vacuum parts, if you think of the coherent state being a superposition of a zero photon state and a tiny amount of population in the single photon state, the dynamics of the zero photon state is trivial. It just doesn't do anything. So in that sense, we can also see this thing as a sort of fast non-trivial contribution to the dynamics of a weak coherent state in the Kaizen nonlinear waveguide. So yes, weak coherent state, and then if you sort of make the intensity a bit higher, then we start to worry about two photon interactions. But in principle, as long as photons that are propagating in the waveguides are not seeing each other, then this treatment, like this dynamical property, should be a universal feature.
Okay, thank you. Any other question? I'm gonna also stop the recording, but we can keep keep in the room and continue discussion. That might just makes it more comfortable for some people.